in this experiment, we use a spirit burner here. In the spirit burner, you will have a substance that will burn. This is what is burning, and this is the delta H of that substance. So you will find, let's say if this is methanol, let's say there's methanol in that spirit burner. So you will find delta H combustion of methanol. So the substance will be in that spirit burner, and this spirit burner is going to heat water in a copper can. So we are assuming that all the energy that is produced by the methanol burning, all this energy is being transferred to the water here, which is going to lead to a change in temperature. So that we can apply Q is equal to MC delta T. So that change in temperature will be delta T. C will be the specific heat capacity of water because we're boiling water here. And M is going to be the mass of water, because if specific heat capacity of water is being used, then the mass should be the mass of the water. So whatever mass of water we use here, or whatever volume of water we use here, this will be equal to M, because remember, density of water is 1 gram per centimeter cube. So mass of water is equal to the volume of water. Now, similarly, like the other experiment, we also have assumptions here, and we are assuming that all the heat from the burner is going into the water. So we are assuming that there is no heat loss to the surroundings. But actually, heat loss is a very important error in this experiment. So not all heat produced by the combustion reaction here goes into the water, because there's air here, so some of the heat is lost to the surroundings. And also the can is going to absorb some of the heat. So we are assuming that the copper can has zero heat capacity. So that's not the case, obviously. So the can absorbs some of the heat, and there's also heat that is lost to the surroundings in that area here. And if you look at the flame, most of the fuels that we use tend to undergo some incomplete combustion, because there's a wick here, and generally incomplete combustion will take place. So in order to minimize heat loss to the surroundings, we are going to place the calorimeter very close to the flame. So usually we try not to have too much space. So you're going to put maybe blocks of wood here to make it close to that can. And then we can also use some form of shielding to reduce any wind. So in this case here, we're using some wood panels to prevent any drought from affecting the heat loss. So let us see now how we can use information from this experiment to find delta H of combustion. So it says that this mass of propanol was burned in a spirit burner, which means that, so in the spirit burner, in that example, you have propanol. So the initial mass of propanol was measured, and then the final mass of propanol was measured after burning. As the propanol burns, the propanol is used up. So the mass of the propanol in the burner is going to decrease. So the final mass is going to be less than the initial mass. So the difference in the two will give you the mass of propanol that was burned in that reaction. So in this case, we have this mass of propanol that was burned. So when you do initial mass minus final mass, this is the mass of propanol that was burned in the spirit burner. And this was used to heat 200 grams of water. So this is the mass. In the calorimeter, the temperature rose by 30 degrees Celsius. This is the delta T. Because you're heating water, we're going to use C of water. And we need to find enthalpy of combustion, delta H. So here we're going to apply Q is equal to MC delta T first. Mass is given 200. C is specific heat capacity of water. And delta T is 30. This will give me my value of Q in joules, which I'm going to convert in kilojoules because delta H is in kilojoules. Now delta H is going to be Q divided by N. I've already found Q and I'm going to divide by number of moles. Now number of moles of what? Number of moles of the substance that was burning. What was burning? It is propanol. So number of moles of propanol will be mass of propanol divided by mol of propanol. Mass is given here. mol is given. I find the number of moles of propanol. So this is the number of moles of propanol that was burnt. So I do minus Q divided by N. I will get delta H. So this is the value of delta H, and you can see here delta H is negative. It must be negative because this is enthalpy of combustion. So this is exothermic, heat is liberated to the surroundings. Delta H must be negative. As homework for this section, you will do number 7 and number 8. This is going to lay the foundations for you to do your practicals this week properly.